Hey, welcome back. This is Verb Ski. Um, 720-985-1986. Keep the text coming. I'm here to help um, extend days, give forgiveness on being late, all that type of stuff. I'll start combing through the grade book here early December, and if you turn stuff in late, try to give your points back. I'm not much of a believer in actual due dates. Have to set them to try to keep everybody on track. But at the same time, this is online. It's very difficult to take online math classes. Plus, if you, well, life just gets in the way. Let's just put it that way. So you'll find that I'm very accommodating at the end. And I'm gonna try my best to actually get back and work all your MMLs. If it wasn't for the hard drive crashing about 3 weeks ago, I'd be in a lot better shape. But here we go. Section 11.4. Trig form of a complex number. Why are we talking about complex numbers? Yeah, remember square root -4? It does not exist in the real number system, but hey, in the complex number system, it's 2i. Um, we get things like this, -1 minus 4i, to be, that's a complex number. It has a real part and an imaginary part. Now, things we used to hate doing, I don't know about you, but I do. When somebody asks me to multiply complex numbers, and you go first term, -3, outer term, plus 2i, inner term, plus 15i, and minus 10i squared. But then you got to remember I squared equals -1. I'll go back and talk about that in a second. But anyway, this is actually plus 10. And you got, therefore, 7 plus 17i is the product of my two complex numbers. So let's derive why I squared is -1. So you know I is the square root of -1. I squared, square root of -1, square root of -1, square root of -1 squared, which is -1. I cubed is I squared times I, so it's -1 I to the fourth, I squared, -1, -1, therefore 1, and then this pattern keeps going forever. I5 is I6, -1, da 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 da. I call this remainder, let me see what I call it. Remainder 1, remainder 2, remainder 3, remainder 0. So when somebody asks me I to the 23, I just simply go 23 divided by 4 because there's 4 in the cycle, and I get a 5, and I get a 20, and I get a remainder 3. So remainder 3 is I cubed, therefore -I. Not that we need this for this section. um, Maybe I'll just say recall. There's dumb stuff like 1 over I. Somebody said you can't have a complex number or an imaginary number in the denominator, so you got to multiply by I over I. And then straight across, you get I over -1, therefore -I. Things like that. So I squared, -1, sorry to go all crazy on you. You know what I used to hate? Dividing complex numbers. And the guy said you can't have an imaginary number at the bottom, so you got to multiply by the complex conjugate. Now the nice thing about conjugates, outer and inners always cancel, so you just really FL it, and you get 25 minus 16i squared, which is really 41. Now, it's better to FL OI, meaning first last. So 10 plus 8i squared, so that's 10 minus 8 is 2. Now do the outer inner, minus 20 minus 10 minus 30i, which is 2 minus 30i. But they go, wait, you can't stop there. You got to break it up. I don't know about you, but I don't call that fun. Once again, it doesn't feel like we're in trig class. This is just an application of trig. I don't want to do this. You know, write it down 4 times. Just don't want to solve it. Just don't feel like doing this. How about I solve all your problems and give you some new ways to do all this stuff? Okay, here we go, new page. Hey, remember first day of class? What we're going to do is create a real axis and an imaginary axis. And we're going to plot some x plus iy, where this is x and this is y. Yeah, that's right. We're going to plot an imaginary point. Now, what I'd like you to think about it as is really imaginary vector, where this is a radius of an imaginary circle, and this is some imaginary angle. Hey, look, back to trig, right? So, whoopsie. So, x equals our cosine theta, because we know cosine theta is x over r, and y equals our sine theta, because we know sine theta is y over r. We know theta ref is inverse tangent of the absolute value of y over x, and if you just did your vector section, I just started off exactly the same, because tangent of theta is y over x. Turns out I'm always going to know what quadrant I'm in, so I'm just going to do a reference angle, and I'm going to remember that. And we call this x plus iy some complex number z, and we want the radius to be the square root of x squared plus y squared. But we don't call it the radius anymore. We call it the absolute value of z, and it's not called the absolute value of z, it's called the modulus. So you know what? Think of the modulus as the radius, just like the magnitude of the vector is really the radius, and you'll be good. But there's nothing new here. But the formulas you're going to get are going to be awesome. So the deal is we got this complex number z, which is x plus iy. But x is our cosine theta, plus I our sine theta, because y is our sine theta. What do you say we factor out an r, and we go cosine theta plus I sine theta? And what do you say we abbreviate it as CIS theta? Yeah, CIS theta. So, compact version of that. I like it a lot. So now we got one way to write down a complex number, but we also got a second way to write down the same complex number. But we're going to get some power in this realm, our CIS theta, which is going to allow us to do things that we can't do very nice in the x plus iy world. So let's not mess around. Let's just get after it. So if you got some z1 to be x1 plus iy1, you got some z2 to be x2 plus iy2, we know there's some modulus z1, which is really the radius z1, and there's some theta 1 associated with the x and the y, where there's some modulus z2, which I'll call r2 because that's what it is, and there's some angle theta 2. Now, nobody likes multiplying complex numbers, because then you got to go back to FOILing. But don't use this RCIS theta 1, replace R1 CIS theta 1, because that's the other form I just came up with, times R2 CIS theta 2. But here's the kicker. Accept this. This answer is just R1 times R2 CIS theta 1 plus theta 2. It's boom, here's the answer. There's no first, outer, inner, last, I squared, -1 business. It is boom, I'm done. So let's look at this right here. So if I'm nice and give you some complex number to be 3 CIS 45 and some complex number Z2 to be 2 CIS 135 without asking any questions, I'll tell you what the product of these are. It's 6 CIS 180. You're like, wait a minute, this doesn't make any sense. Well, let's make it make sense. C is cosine 180 plus I, S is sine 180. This is 6 cosine 180 -1 plus I sine 180 0 is 6 times -1 -6. You're like, well, I didn't learn anything, but I can do that. Easy enough. I just multiply the radiuses, add the angles, get here, do that. I can do that, but what did I actually do? Let's see what 3 CIS 45 really is. So what they're really asking us is to do 3 cosine 45 plus I sine 45 times 2 cosine 135 plus I sine 135. What they're really asking us to do is the square root of 2 over 2 plus I, the square root of 2 over 2 times 2. Cosine of 135 is negative the square root of 2 over 2 plus I, the square root of 2 over 2. Then obviously we would multiply that and get 6. But then we gotta first it. Whoa. And then we gotta outer it, and we gotta inner it, and we gotta last it. I just don't feel like doing it. It looks hard. So, you know what we're gonna get? We're gonna get -6. But I would much rather use CIS than traditional. So the trick is you should try to convert things into CIS. Here's a good example. So if somebody just happens to give you, you got to understand these got to be pretty cooked up. So how about, maybe I can actually find one in the book and make it easier on me. Maybe. No, they don't make it easy on me. Okay, let's do this. X and Y. So this is going to be dumb, guys. 1/2 minus the square root of 3 over 2I times minus the square root of 3 over 2 minus 1/2 I. These are unit circle numbers, where x is 1/2, and we get negative the square root of 3 over 2. So we know the radius is 1, and we know this guy here, the angle is 240 degrees. Whew! This guy is over here and down here 1/2. So this is 210 degrees. Since it's a unit circle number, we know the radius is 1. So I don't know about you, but I don't want to multiply these two things together. But I do know the top one is 1 CIS 240 times 1 CIS, first, 240 and 210. I don't think 240 is right, though. That'd be 300. There we go. Something wasn't registering. 300. So you multiply your radiuses. 1 CIS 510 is the answer. Now, do I know 510? Well, what's 510 minus 360? 0, 5, 4, 1, 5, 150, which is 1 CIS 150, which is cosine 150 plus I sine 150, which is minus the square root of 3 over 2 plus 1/2 I. You got to understand it's kind of dumb, but at the same time, you know, it is kind of cool. All right, next formula. If I give you z to be x1 plus iy1, which is r1 cis, which is really r1 cis theta 1. And if I would like to go x1 plus iy1 to the n, which is no fun, to the n, write it down, n times multiply, like cube to the 4th. It's r1 cis theta 1 to the n. This is easy to do. Good, because I didn't want to do this. It's r1 to the n cis to the n theta 1. You're like, crazy. Okay, so how about this? 4 radical 3 plus 4i. Let's let be z. Now, we know x is 4 radical 3 and y is 4. And we know theta ref, by the way, this is plus and this is plus, so we're in the first quadrant, an imaginary first quadrant, but it's inverse tangent absolute value of y over x, which is inverse tangent of 1 over the square root of 3, and then that should set off alarm bells, because that's inverse tangent of the square root of 3 over 3, and I know my unit circle very well. I know when tangent is the square root of 3 over 3, it's at 60 degrees. Oh, that would be 30 degrees. There we go, 30 degrees. So I know the radius is the square root of 4 radical 3 squared plus 4 squared, because the radius is the square root of x squared plus y squared, which is the square root of 16 times 3 plus 16, which is the square root of 64, which is 8. So z can be rewritten as 8 CIS 30 degrees. Well, what about z cubed? What about 4 radical 3 plus 4i cubed? I do not want to do this, but I do want to do this. because the answer is 8 cubed CIS 3 times 30, 90. Piece of cake. 8 cubed cosine 90 plus I sine 90. Cosine 90, 0. Sine 91. 8 cubed 0 plus 1i. The answer is 8 hat 3. 512. Boom. Awesomeness. Okay. How about the problem z1 divided by z2? We don't want to do x1 plus I y1 divided by x2 plus I y2, because you always got to multiply by the conjugate. Well, how about let's just use R1 CIS theta 1 and R2 CIS theta 2. Well, the answer is just R1 over R2 and then CIS theta 1 minus theta 2. I like this. This is fast. You just look at it and write it down. So here's an example. 16. Oops. Okay. Let's pause this bad boy. Okay, I think I'm back. I thought I had crashed. That would have been terrible. So let's look at 16 cosine 300 plus I sine 300, which is CIS notation. The book doesn't like get after it hard enough. Cosine 60 plus I sine 60. Once again, that's really 16 CIS 300 over 8 CIS 60, which is 2 CIS 240, which is easy. 2 cosine 240 plus I sine 240, which is 2. It's like cosine of 60, you're in the third, therefore negative, therefore 1/2 minus square root of 3 over 2. I bring in the 2's, 1 plus square root of 3. I bring in the, oops, negative, negative. Do I like that? No, not really. Here's it's kind of hard to justify, but here's one that's pretty cool. It's no fun unless it's a unit circle number. So here's a problem I definitely do not want to do. But you really only want to do this CIS stuff if there's unit circle numbers. So you got to call the top one Z1. You got to call the bottom one Z2. So you're hoping that the angles are nice. So go theta is inverse tangent of the y value over the x value, and don't use that stupid negative. It's inverse tangent of the square root of 3, which is 60 degrees, and that's a reference angle, but you are, x is negative, y is positive, you're in the second, so theta is really 120, and you're feeling happy about that, and we'll call that theta 1. Now the magnitude's easy, so let's not worry about that. Let's go find theta 2. Theta ref is inverse tangent. You take the y value, which is the square root of 2, over the square root of 6, and that's inverse tangent, 1 over the square root of 3, and I know that to be 30. Therefore, unit circle number, you're feeling good. This is plus, 30 is actually theta 2. Now you got to figure out the radius, R1, which is the square root of negative 3 radical 2 squared plus 3 radical 6 squared, which is the square root of 9 times 2, 18, plus 9 times 6, 6. 9 times 6, 54, 64, 70, square root of 72. Okay, which is 9 times 8, no, 36 times 2, 6 radical 2. And this guy, R2, is the square root of square root of 6, square root of 2, square root of 6 squared plus the square root of 2 squared, which is the square root of 6 plus 2, square root of 8, which is 2 radical 2. Pause. Okay, now that we did all the work, we got, let me see here. Let me see if struggling with the slider bar. So we got Z1 with theta 1 being 120 and the radius being 6 radical 2. So we got 6 radical 2 CIS 120 over 2 radical 2 CIS 30, which equals 3 CIS 90, which equals 3 cosine 90 plus I sine 90, which equals 3, 0 plus I1 equals 3I. Wow. Pretty cool stuff. Pretty neat stuff. All right. Well, basically I taught you everything I think I need to teach you. Where does the book go next? Next is we're on the same topic. It's powers and roots of complex numbers. So basically, I gave you a lecture that is I'm already went through one of the formulas. So I think I'll be good for a recap. So I'm going to end this one, and basically you'll get just a tiny bit of overlap in the next section 11.5. Once again, another pretty good section. It's over complex numbers, so the nice thing is it doesn't feel connected, and it's just using 3 or 4 formulas. So all you really need to know how to do is, transform into the other form and then use the formula. So, and they'll all be perfect. They all perfectly work out just like the lecture did. You'll get all unit circle type things. So life will be good. All right, I'm going to stop this lecture.